Hello, my friend. Tonight we're exploring one of the strangest objects the universe has ever made. A dead star so extreme that it can bend our understanding of matter, energy, and reality itself. A magnetar. Magnetars are nothing like ordinary stars. They are not glowing spheres of gas quietly burning in the dark, but compact remnants made of matter so crushed and so exotic that we cannot see anything like it in everyday life and cannot truly create it here on Earth. Magnetars are small, distant, and almost invisible, yet they can unleash forces more powerful than almost anything else in the cosmos. Somewhere inside their story is an answer to how far nature can push matter before it becomes almost unrecognizable. And the deeper we go, the more these dead stars begin to feel less like distant objects and more like hidden cracks in our ordinary picture of the universe. To understand them is to step into a part of physics that feels far removed from everyday life and reveals something deep about the rules that shape everything around us. So tonight, if your mind needs somewhere peaceful to wander, and if sleep feels just a little far away, you are in the right place. Let's settle in together and take a calm journey into one of the most extreme corners of the cosmos. Chapter 1. What a magnetar really is. Few objects in the universe show more clearly how strange and exciting reality can become than a magnetar. A dead star so extreme that it turns familiar physics into something almost unrecognizable. A magnetar is a special kind of neutron star. It is not an ordinary star still shining by burning fuel in its core like our sun. It is what remains after a much larger star reaches the end of its life, collapses under its own weight, and explodes. The outer layers are blasted away into space, while the core is crushed into one of the densest objects nature can make without forming a black hole. If that compact remnant is born with an especially powerful magnetic field, astronomers call it a magnetar. To understand why this matters, it helps to begin with something simple. Stars live in a balance. Gravity pulls inward. Pressure from nuclear fusion pushes outward. For a very long time, those effects can oppose each other. But that balance does not last forever. When a very massive star runs out of the right kind of fuel in its core, gravity begins to win. The center collapses. Matter falls inward. Pressure rises enormously. Electrons and protons are forced together, forming neutrons. In a brief and violent transition, the heart of the star is transformed into a neutron star. A neutron star is already an extreme object. It contains more mass than the sun packed into a sphere roughly the size of a city. It is no longer a giant ball of gas. It is a compact remnant with a solid outer crust, an interior under crushing pressure, and gravity so strong that its surface would feel nothing like the surface of any world we know. If you stood near one, which of course you could not survive, even light would have a harder time escaping its gravity than it does from an ordinary star. Time itself would pass a little differently there than it does far away. A magnetar belongs to this family, but it sits at the most magnetic and violent end of it. What makes it special is not simply that it is dense, hot, and compact. What makes it special is that its magnetic field is vastly stronger than that of Earth, stronger than that of the Sun, and far stronger than the magnetic fields of typical neutron stars. In ordinary life, magnetism can seem gentle and familiar. It lets a compass point north and helps run motors, speakers, and generators. In a magnetar, magnetism is no longer a quiet background feature of matter. It becomes one of the main forces shaping the object's entire behavior. That is why magnetars are often described as the strongest magnets known in the universe. Their magnetic fields are not just impressive by human standards, they are extreme even by astrophysical standards. Around a magnetar, the field is strong enough to dominate the star's surroundings, twist charged particles, channel radiation, and store enormous amounts of energy. In many cases, astronomers think the magnetic field is the main power source behind the star's outbursts. A normal star shines because fusion releases energy. A magnetar can release huge bursts of energy because its magnetic field itself is under strain, slowly changing, twisting, and sometimes violently rearranging. This is one of the key ideas to understand from the start. A magnetar is not just a dead star with a strong magnetic field attached to it, as if the field were only a detail. The field is central to the story. It shapes the star's radiation, its outbursts, its spin, and much of the strange behavior that makes magnetars so interesting. Without the extreme magnetic field, you would not have a magnetar anymore. You would have some other kind of neutron star. Even the surface of such an object is difficult to imagine properly. On Earth, matter behaves according to conditions our bodies evolved to understand. Solids feel solid. Atoms keep their ordinary structures. Gravity is mild enough that a person can stand and move without thinking about the pressure of their own weight. On a magnetar, nearly everything is pushed into a different regime. Gravity compresses the star into a compact sphere. The crust is thought to be rigid and immensely stressed. The magnetic field threads through the crust and out into space, and those parts of the system are linked. If the crust shifts, the field can shift with it. If the field twists, the crust can be strained until it cracks. This is why magnetars can experience what astronomers call starquakes, fractures in the crust that release extraordinary amounts of energy. When a magnetar becomes active, it can emit bursts of X-rays and gamma rays. Sometimes these are short and sharp. Sometimes the activity can continue much longer. On rare occasions, a magnetar can produce a giant flare, an eruption so powerful that it can briefly outshine almost everything else in the high-energy sky. These outbursts are one reason magnetars were recognized as a distinct class of object. They do not merely sit in silence as dense stellar leftovers. They flare, tremble, brighten, fade, and sometimes surprise astronomers with behavior that forces theories to improve. In that sense, magnetars are not only fascinating objects, they are laboratories. Human beings cannot create these conditions on Earth in any lasting way. We cannot compress matter to neutron star density, and we cannot generate magnetic fields on this scale in a stable object. But the universe can. Because it can, astronomers are able to study matter, radiation, gravity, and magnetism in combinations that push theory to its limits. A magnetar is a place where ideas from nuclear physics, quantum physics, relativity, plasma physics, and stellar evolution all meet in one small remnant. That is one reason the topic feels so fundamental. When you ask what a magnetar really is, you are not only asking about a strange type of star, you are asking what matter does when it is crushed to extremes. You are asking how magnetic fields store and release energy. You are asking how stars die, what remains after that death, and how the laws of physics behave under pressures far beyond ordinary experience. It is also important not to confuse a magnetar with a black hole, because both are born from stellar catastrophe, and both belong to the family of extreme remnants. A black hole forms when collapse goes so far that no known force can stop it before an event horizon appears. A magnetar does not go that far. It remains a physical object with a surface, a crust, and a magnetic structure extending into space. Because magnetars have surfaces and magnetic fields that affect the radiation we detect, they give astronomers a chance to study an extreme state of matter that is still, in a sense, visible. Another useful comparison is with pulsars. A pulsar is a neutron star whose radiation sweeps across space in a beam as the star rotates, creating pulses when the beam crosses our line of sight. Some magnetars can also pulse because they too rotate and emit radiation. But as a broad rule, pulsars are usually discussed in terms of rotation and beam geometry, while magnetars are discussed in terms of magnetic stress, high energy outbursts, and magnetic decay. A magnetar is therefore both part of the neutron star family and something unusually specialized within it. There is another layer of wonder here. A magnetar is tiny on the scale of astronomy. It is far smaller than a normal star, far smaller than a planet, and compact almost beyond intuition. Yet this small object can dominate its surroundings with astonishing intensity. That is one of the quiet lessons of astrophysics. Size alone does not determine importance. Astronomers have identified only a small number of confirmed magnetars, which tells us something important too. These are not common everyday stars. They seem to represent a rare path in stellar evolution, one that requires the right starting conditions and then leaves behind an object that does not remain in its most active state forever. Some may spend long periods relatively quiet before erupting again. Others may gradually lose the magnetic energy that makes them so distinctive. And yet temporary does not mean unimportant. Some of the most illuminating events in astronomy are not those that last the longest, but those that reveal the most under extreme conditions. A magnetar flash can tell us something about the strength of a crust we can never touch, the structure of a field we can never see directly, or the way a dead star rearranges itself after internal stress becomes too great. Magnetars may also help explain other mysteries. They are now leading candidates for at least some fast radio bursts, those brief and powerful flashes of radio energy that arrive from distant galaxies. For now, the simplest truthful answer is this. A magnetar is the collapsed core of a once massive star, reborn as a neutron star whose magnetic field became extraordinarily powerful. It is dense beyond ordinary imagination, physically small but enormously massive, and capable of releasing tremendous energy through the stress and decay of magnetism itself. It is not powered like an ordinary star, and it does not behave like a quiet remnant. It is a compact object in which gravity, nuclear matter, and magnetic energy are all pushed toward extremes. As this chapter comes to a close, it helps to hold on to that image without forcing it to become fully familiar. Somewhere in the darkness, there are dead stars that did not end in silence. They remain tense, magnetic, and restless, carrying within them the memory of stellar collapse. And for tonight, you do not need to solve all of that strangeness. You only need to let it drift gently through your mind, like a distant signal crossing a calm and silent sky. Chapter 2. How a massive star dies. A massive star does not simply fade away when its life ends. It passes through one of the most dramatic transformations in nature, turning the steady glow of starlight into a collapse powerful enough to remake everything around it. To understand how a massive star dies, it helps to begin with the basic balance that governs all stars. Gravity pulls inward, trying to squeeze the star tighter and tighter. Heat and pressure from nuclear fusion push outward, resisting that squeeze. As long as those effects remain in balance, the star can shine steadily. Death begins when that balance can no longer be maintained. A massive star is born from a cloud of gas and dust. Gravity slowly gathers material together until the center becomes dense and hot enough for fusion to begin. Hydrogen nuclei combine into helium, and energy begins flowing outward. That energy does not escape instantly. It works through the star and eventually leaves as light and heat. For a while, this outward pressure keeps gravity from crushing the star any further. But a massive star is not just a larger version of a star like the Sun. The greater the mass, the greater the pressure in the core, and the higher the temperature must become to support the weight above it. That means fusion runs much faster. A massive star may begin life with far more fuel than a smaller star, but it consumes that fuel at a much more extravagant rate. In a sense, it lives fast because gravity forces it to. It shines more brilliantly, burns more fiercely, and reaches old age much sooner. For much of its life, the star is powered by hydrogen fusion in its core. From the outside, this can look like a stable stage, but every reaction is slowly changing the core itself. Hydrogen is converted into helium, and over time the central hydrogen supply is depleted. Once there is no longer enough hydrogen fusion in the core to fully support the star, gravity begins to tighten its grip. The core then contracts, and as it contracts, it heats up. This is one of the most important ideas in stellar evolution. The end does not begin as a simple shutdown. Often, the loss of one source of fusion creates the conditions for another. As the core grows hotter and denser, helium fusion can begin. The star gains a temporary reprieve. Outward pressure rises again for a time, and the outer layers swell enormously. The star becomes a red supergiant, vast in size and brilliant in luminosity, even though its outer surface is cooler than before. Inside that red supergiant, the structure becomes much more complex. Once helium in the core is exhausted, contraction begins again, temperature rises again, and if the star is massive enough, the core can ignite heavier fuels. Carbon can fuse into heavier nuclei, and then still heavier stages can follow. Oxygen, neon, silicon, and other burning phases may appear in sequence as the star struggles to resist gravity. The interior develops a layered structure with different shells around the center, producing energy from different fuels at the same time. That layered structure is a sign that the star is nearing its end. A smaller star cannot usually push this process very far because its core never becomes hot enough to ignite so many successive stages. But a massive star can keep forcing itself onward, turning its interior into a chain of increasingly demanding reactions. Each stage releases energy for a shorter time than the one before it. Early life can last millions of years, but the late stages accelerate dramatically. The closer the core comes to iron, the more quickly the remaining time is consumed. Iron marks a turning point in the life of the star. Fusion is not an endless source of usable energy. For lighter elements, fusion can release energy and help support the star. But iron is different. Once the core becomes dominated by iron, fusion can no longer provide the net energy needed to hold gravity back in the same way. The star has reached a dead end. Gravity is still pulling inward with enormous force, but the core can no longer unlock enough energy through fusion to resist collapse. At that stage, the final crisis begins. The iron core is held up only briefly by forms of pressure that cannot withstand unlimited compression. As gravity drives the core inward, the conditions become extraordinary. Atoms are crushed apart, electrons are driven into protons, matter is forced into a much denser state. The core, which took millions of years to build and only a short time to race through its final burning stages, now collapses in far less than a heartbeat. This collapse is not a gentle shrinking. It is a catastrophic inward plunge. The central part of the star falls so quickly that ordinary atomic structure breaks down. The collapsing core becomes incredibly compact. Then, when the density rises high enough, the deepest region resists further compression much more strongly. The collapse abruptly slows there, while material above is still crashing inward. That sudden change helps create a rebound and a shock wave that tries to move outward through the rest of the star. For a long time, the basic picture of stellar death was described as a simple bounce followed by an explosion. The deeper reality is more complicated. The shockwave forms, but it can lose energy as it moves through the dense interior. Some of that energy goes into breaking apart heavy nuclei. Vast numbers of neutrinos are also produced during collapse, and they carry away enormous energy. For a moment, the shock can stall instead of immediately blasting the star apart. What happens next is one of the most important parts of supernova physics. The newborn compact core is flooded with neutrinos. Although neutrinos interact only weakly with matter, there are so many of them and the conditions are so extreme that a small fraction of their energy can be transferred to the surrounding material. That extra energy is thought to help revive the stalled shock. Convection, turbulence, and uneven flows inside the dying star may also help. When the process succeeds, the result is a core collapse supernova. A core collapse supernova is not merely a bright flash. It is the star's outer layers being violently expelled into space. The explosion sends matter rushing outward at enormous speed. Elements forged over the star's lifetime, along with new nuclei produced during the blast itself, are scattered into the surrounding gas between the stars. In that sense, the death of a massive star is also an act of enrichment. Material needed for future stars, planets, and complex chemistry is spread by these explosions. Yet the explosion does not always destroy everything at the center. What remains depends mainly on how massive the core is after collapse. If the remnant core falls within a certain range, it can settle into a neutron star. If it is too massive, collapse continues and a black hole forms instead. This branching point matters deeply for the story of magnetars, because a magnetar begins not with the whole star, but with the compact core left behind after the rest has been blasted away. The formation of that compact remnant is the true ending of the star and the beginning of a new object. The fusion-powered star is gone. Its long struggle against gravity has ended. In its place is either a neutron star or a black hole, surrounded by expanding debris from the explosion. That debris can glow for thousands of years as a supernova remnant, carrying traces of the star's former interior into space. From a great distance, a supernova can briefly rival the light of enormous stellar populations. But the brightness is only the visible sign of a deeper process. What has really happened is that the star exhausted the available ways to support itself through fusion. Step by step, gravity kept forcing the core into hotter and denser states, demanding new fuels each time. Eventually, the star reached a stage where there was nowhere left to go. The support failed, the core collapsed, and the rest of the star was swept into the consequences. Not every massive star dies in exactly the same way. Mass, rotation, composition, and the presence of a companion star can affect the final outcome. Some lose much of their outer material before collapse. Some may produce a weaker visible explosion. Some leave rapidly spinning remnants. But the central logic remains the same. A massive star dies because gravity eventually overcomes the pressure that fusion can provide. That is why the death of a massive star matters so much in cosmic history. These stars do not merely shine and vanish. They manufacture heavy elements, stir and enrich galaxies, and leave behind some of the strangest objects in the universe. A pulsar, a magnetar, or a black hole is not separate from this story. Each is a continuation of it, a different answer to the same final question. What remains when fusion can no longer hold up a giant star? So when we speak about the death of a massive star, we are really speaking about the breaking of a balance. For millions of years, gravity and pressure coexist in a tense agreement. Then, fuel by fuel, that agreement begins to fail. The core contracts, the star swells, heavier elements ignite, and the inner structure becomes more desperate and unstable. At last, the core reaches iron, the road ends, and the star falls inward. In that collapse, the ordinary light of stellar life is transformed into one of the most violent events in the universe. And yet, seen from far enough away, even this violence belongs to a larger calm. A massive star lives by balance, dies by imbalance, and in dying returns its substance to the cosmos. You can let that thought settle gently now. Even the brightest stars do not vanish without meaning, and high above the noise of the day, the universe continues in patient, silent order. Chapter 3. The Birth of a Magnetar. The birth of a magnetar begins at the precise moment when a dying star leaves behind something far stranger than an ordinary remnant. A newborn object so dense, so fast, and so magnetically intense that it may spend its early life reshaping itself from the inside out. By the end of the previous chapter, the massive star had already reached its final crisis. Its core had collapsed, the outer layers had been blasted away, and the old fusion-powered star was gone. What remains after that event is not automatically a magnetar. First, there is a newborn neutron star, still extremely hot, still settling, and still adjusting to the violence of its own formation. In many cases, that remnant will become an ordinary neutron star or a pulsar. Only in a smaller set of cases does it become something more extreme. Chapter 3 is about that narrow path. A useful way to think about magnetar birth is to imagine that several difficult conditions have to come together at once. The remnant must already be a neutron star, which means the collapsing core did not become a black hole. It must also inherit or generate an unusually powerful magnetic field. And in the most widely discussed formation picture, it must be born rotating extremely rapidly, fast enough for the first moments of its life to behave very differently from those of a more ordinary remnant. The question is not simply why neutron stars have magnetic fields at all. The deeper question is why a few of them begin life with fields so immense that magnetism becomes the defining feature of the object. One part of the answer is simple compression. Before collapse, the core of the massive star already has some magnetic field. When that core is crushed from stellar size down to the size of a city, the same magnetic flux is squeezed into a vastly smaller volume. That alone can amplify the field dramatically. This idea is straightforward and important, and it almost certainly contributes to the result. But many researchers think compression by itself is not enough to explain the strongest magnetars. It may be part of the story without being the whole story. To create the most extreme fields, something more may have to happen in the first seconds after the neutron star forms. That additional ingredient is often described as a dynamo. On Earth, the magnetic field of our planet is maintained by motion in its liquid outer core. In stars, magnetic fields can also be strengthened by flowing, conducting material. A newly born neutron star is not a quiet object. It is hot, turbulent, and in motion. If it is rotating fast enough, those internal motions can organize themselves in ways that rapidly build a far stronger global magnetic field. In this picture, the neutron star is born not merely with a compressed version of the old core's field, but with a field that is actively amplified by violent internal motion during its earliest moments. Rotation matters because rotation gives structure to chaos. A slow newborn neutron star may still be violent and convective, but its internal motions are less effective at building a huge, ordered magnetic field. A very rapidly rotating one behaves differently. Rotation can help stretch, wind, and reinforce magnetic field lines, turning a turbulent interior into a powerful magnetic engine. This is why fast spin is so often treated as central to magnetar birth. In the leading scenario, a magnetar begins life spinning extraordinarily quickly and then loses that rotational energy very efficiently because its magnetic field is so strong. In other words, it may be born as both a fast spinner and a supermagnet, but it does not stay a fast spinner for long. That early loss of spin is itself an important clue. If a newborn neutron star has a colossal magnetic field, the field can act like a brake. Rotational energy is transferred away, and the star slows down much more rapidly than a weaker field neutron star would. This means the most dramatic part of magnetar birth may happen almost immediately, in a stage that passes quickly on astronomical timescales. By the time astronomers observe the object later, it may no longer be spinning with the frantic speed it had at the moment of birth. What remains visible is the aftermath. A slower neutron star whose magnetic field is still enormous and whose later behavior is powered largely by the decay and rearrangement of that field. There is another subtle point here. When scientists talk about the birth of a magnetar, they are not only talking about making a strong field. They are also talking about the shape of that field. Magnetic structure matters. A field can be tangled inside the star, wound up like a twisted spring, or organized into larger patterns that reach far into space. The way the field is arranged affects how the star evolves, how stresses build in the crust, and how energy is later released. So the birth of a magnetar is not like placing a simple bar magnet inside a dead star. It is the creation of a complex magnetic architecture that may continue shifting long after the collapse itself is over. This is one reason magnetar birth is still an active scientific problem rather than a fully finished story. Astronomers know that magnetars exist. They know these objects are neutron stars with extraordinary magnetic fields. They know their later activity is tied to magnetic strain, magnetic decay, and violent releases of stored energy. But the exact route from collapsing stellar core to mature magnetar is still being studied. Some evidence points strongly toward the rapid rotation dynamo picture. Other work explores whether the magnetic field of the progenitor star might already have been unusually strong and then amplified during collapse. These ideas are not always opposites. nature may use more than one route, or different routes may matter in different cases. That possibility becomes even more interesting because not every magnetar may come from the same kind of birth event. The standard picture begins with the collapse of a massive star, and that is likely the main route. But there are also hints that some magnetars may form through other channels. A merger of two neutron stars may in some cases leave behind a magnetar remnant rather than an immediate black hole. Another proposed route is the collapse of a white dwarf in a binary system after it gains enough mass from a companion. These alternatives are not thought to replace the main formation story, but they widen the picture and remind us that extreme objects do not always have only one origin. Even within the ordinary core collapse route, the original massive star may influence the outcome in several ways. Its mass matters, but mass alone is not enough. Rotation before collapse may matter. The strength and geometry of the magnetic field inside the progenitor may matter. Whether the star has a close companion may matter, because binary interaction can strip matter away or alter angular momentum. So when we ask why one collapsing core becomes a typical neutron star and another becomes a magnetar, the answer may depend on a whole chain of earlier stellar history, much of it hidden from direct view. The remnant we finally observe is like the last line of a story whose earlier chapters have mostly disappeared. What is clearer is what happens after birth. Once the magnetar exists, it begins a new phase of life powered less by ordinary rotation and more by magnetic evolution. The field inside and around the star is so intense that it can slowly distort the crust, heat parts of the surface, twist the magnetosphere, and store energy that may later be released in bursts and flares. This later activity belongs to future chapters, but it starts with the birth conditions established here. A magnetar is what you get when the newborn neutron star enters life with magnetism strong enough to dominate almost everything that follows. There is also something profound in the timing of all this. The massive star spends its long life building toward collapse, but the decision about whether its remnant becomes a magnetar may be made in an astonishingly short interval during and just after that collapse. In a tiny window of time, compression, turbulence, neutrino-rich convection, and rotation combine inside matter denser than anything familiar. A slight difference in starting conditions may help determine whether the object will become a relatively ordinary neutron star or one of the strongest magnets in the cosmos. The quiet star of the past is gone, and in its place, a new identity is set almost instantly. So the birth of a magnetar is not a separate event from stellar death, but a special outcome within it. A massive star collapses, a neutron star is born, and then, under rare and extreme conditions, that neutron star emerges with a magnetic field amplified far beyond the norm. Compression likely helps. Rapid rotation likely helps. Internal fluid motion may act as a dynamo. The newborn field may be twisted, wound, and unstable from the beginning. Over time, the object settles, slows, and begins the strange magnetic life that makes magnetars so distinctive. If Chapter 2 was about the end of a star, Chapter 3 is about how an ending becomes a transformation. The star does not merely die and leave behind a silent core. Under the right conditions, it creates a remnant that carries the collapse forward in another form. Its fusion is over, but its story is not. The violence of the collapse has been compressed into magnetic structure, rotational energy, and hidden internal stress. From that point onward, the object will not live like a star. It will live like a magnetar. And there is something oddly calming in that thought. Even in one of the universe's most violent transitions, the result is not chaos without pattern, but a new order taking shape. A massive star falls inward, and from that collapse, a rarer kind of object is born, small, dense, and quietly carrying unimaginable power into the dark. Chapter 4. Inside a Star Crushed Beyond Imagination. To understand a magnetar fully, it is not enough to know that it was born from a dead massive star. At some point, you have to ask what actually exists inside such an object, and that question leads into one of the strangest places in all of physics, where matter is compressed so severely that the familiar structure of the world begins to break down. A magnetar is a type of neutron star, and a neutron star is not simply a star made smaller. It is matter forced into a completely different state. In ordinary life, nearly everything we touch is made of atoms with empty space inside them. Electrons move around atomic nuclei, and the space between particles is part of what makes normal matter behave the way it does. A neutron star exists because that roomy atomic structure has been largely crushed out of existence. Gravity has done what no ordinary environment can do. It has pressed matter inward until the distinction between separate atoms no longer matters in the same way. That is why the inside of a neutron star is so difficult to imagine honestly. Human intuition was built for mountains, oceans, clouds, metal, wood, and air. It was not built for matter with the mass of a star packed into an object only a little larger than a city. A magnetar is not a scaled-up version of something familiar. It is a place where pressure, density, and gravity have all crossed into a regime that the rest of the universe rarely shows openly. Even its surface is not really a surface in the everyday sense. A neutron star is thought to have a very thin atmosphere, only a delicate outer layer compared with the size of the star itself. This atmosphere may contain light elements such as hydrogen or helium, or in some cases heavier elements depending on the star's history. Beneath that thin outer skin lies the crust, and the crust is where matter first begins to look profoundly unfamiliar. In the outer crust, atomic nuclei still exist, but the pressure is already so intense that electrons are no longer bound to them in the ordinary way. Instead of neat individual atoms, there are bare nuclei packed closely together in a sea of free electrons. The matter is solid, but not like rock or metal on Earth. It is a dense lattice of nuclei held in place under crushing gravity, with electrons moving through it. In a sense, the crust is a kind of ultra-compressed matter that still preserves a faint memory of atomic structure, even though normal atoms are gone. As one moves deeper, the pressure rises further, and eventually the nuclei can no longer contain all their neutrons. Some of those neutrons begin to leak out. This transition marks the inner crust, where the material becomes stranger again. Now the crust contains nuclei, free electrons, and also a growing population of free neutrons. Those neutrons are not simply scattered particles drifting in empty gaps. They form a dense component of the matter itself, and under the conditions inside a neutron star, they are believed to behave collectively in remarkable ways. One of the most important ideas in neutron star physics is that some of the matter inside does not act like an ordinary fluid at all. Many models indicate that the neutrons in parts of the interior form a superfluid, A superfluid is a state of matter that can flow with almost no internal friction under the right conditions. This is not exotic only in a poetic sense. It means that the interior of the star may contain matter moving according to quantum rules on a large scale, with behavior that differs sharply from that of everyday liquids. In some regions, protons may also form a superconducting state, meaning that electric currents can persist in a way very different from normal conducting matter. These possibilities matter because they help explain why neutron stars do not always behave as simple rigid spheres. In some neutron stars, sudden changes in spin have been observed. One leading explanation involves interactions between the solid crust and a superfluid interior that does not always stay perfectly locked to it. In a magnetar, where the crust is also under powerful magnetic stress, the internal structure becomes even more important. The inside is not just dense, it is dynamic, layered, and capable of storing strain in ways that can later affect the whole star. Below the inner crust lies the core, and this is where certainty becomes harder. The outer part of the core is generally understood as matter made mostly of neutrons, with a smaller number of protons and electrons mixed in. At these depths, the distinction between one nucleus and another has disappeared completely. There is no iron, no calcium, no ordinary periodic table as we know it. Instead, there is a continuous sea of densely packed particles under pressure, so extreme that the matter is balanced at the edge of further collapse. This balance is one of the quiet miracles of neutron stars. Gravity is trying to crush the object even more, but the matter resists. Part of that resistance comes from quantum rules that prevent identical particles from being packed into exactly the same state. Part of it comes from the strong interaction that governs the behavior of particles inside atomic nuclei. These effects together provide a kind of pressure that stops the star from collapsing further, at least if the star is not too massive. In that sense, a neutron star is a frozen contest between gravity and the deepest rules of matter. But that still leaves the deepest question unanswered. What happens in the innermost core at the highest densities of all? This is where modern astrophysics becomes especially careful, because scientists do not yet know with full confidence what state matter takes there. It may remain mostly neutron-rich, or the pressure may become so great that new forms of matter appear. Particles containing strange quarks may emerge, or the neutrons themselves may lose their identity and dissolve into a dense soup of quarks. These are not wild fantasies. They are serious physical possibilities, but the evidence is still incomplete. This uncertainty is one reason neutron stars are so valuable to science. The inner core cannot be visited, sampled, or recreated in a laboratory for more than the briefest instant under very different conditions. So astronomers have to infer its nature indirectly. They study the masses and radii of neutron stars, the way these stars cool, the way they vibrate, the way they spin, and the way light escapes from their surfaces. From those clues, they try to learn how compressible the matter inside must be. If matter is relatively stiff, a neutron star can stay larger for a given mass. If matter is more compressible, the star becomes smaller. That is why measuring size and mass with high precision is so important. Those measurements are not just about the outside. They are one of the few ways to learn what is hidden within. The gravity of a magnetar also changes how the outside world sees the inside. Near such a compact object, space and time are strongly warped. Light leaving the surface loses energy as it climbs away from the star's gravity. Light from parts of the far side can even be bent toward us, allowing more of the surface to be visible than ordinary geometry would suggest. So even when astronomers observe radiation from the surface, they are not seeing it in a simple or direct way. The star's gravity modifies the message before it reaches us. That same gravity has another consequence. The pressure inside the star rises extraordinarily quickly with depth. On Earth, a person can imagine diving into the ocean, where pressure increases steadily as water piles up above. In a neutron star, that familiar intuition fails almost instantly. The weight of the overlying layers is so immense that the material below is squeezed into states with no analog in daily experience. The crust itself, though thin compared with the whole star, supports extraordinary stresses. Deeper down, the core reaches densities comparable to or greater than those inside atomic nuclei. Matter is no longer arranged into little islands of structure. It becomes a continuous ultra-dense medium. Some theories suggest that in a narrow region near the base of the crust, matter may take on bizarre intermediate shapes before the core begins fully. Instead of simple spherical nuclei, the competition between nuclear attraction and electric repulsion may favor elongated, flattened, or tangled forms. Because some of these shapes resemble familiar foods when drawn schematically, physicists have given them playful names, but the underlying idea is serious. Matter may reorganize into unusual geometries as it is forced across the boundary between crust-like and core-like behavior. This region could influence how heat flows, how the crust breaks, and how the star responds to disturbance. Temperature, surprisingly, does not rescue the star from this strange state. A newborn neutron star is incredibly hot by human standards, but compared with the energies binding its matter under such pressure, it quickly becomes a relatively cold object in a physical sense. That is why quantum behavior such as superfluidity can emerge. The star is hot enough to shine in high-energy light, yet cold enough relative to its internal scales for collective quantum states to matter. This combination is one of the reasons neutron stars are such extraordinary natural laboratories. They unite gravity, nuclear physics, thermal physics, and quantum behavior in one object. All of this means that when we picture the inside of a magnetar, we should not imagine a hollow cavity, a furnace of ordinary gas, or a miniature version of the sun. We should imagine a layered compact world, a thin atmosphere, a solid outer crust of nuclei and electrons, a deeper crust where neutrons begin to escape and move collectively, an outer core dominated by dense nuclear matter, and an inner core whose true composition remains one of the great open questions in astrophysics. It is a structure built not by chemistry, but by pressure. And perhaps that is the deepest shift in perspective this chapter offers. On Earth, matter is mostly organized by electromagnetism and chemistry. Atoms form molecules, molecules form materials, and materials build the visible world. Inside a magnetar, gravity and nuclear physics take over. Chemistry disappears as the main architect. The ordinary language of substances gives way to the language of states, phases, and interactions under compression. A magnetar is what matter becomes when the universe stops asking what atoms can build and starts asking how much pressure matter itself can endure. So inside a star crushed beyond imagination, there is no hidden chamber of fire, no quiet empty center, and no familiar substance waiting to be recognized. There is only matter pushed to the threshold of what nature allows, arranged in layers that are part solid, part fluid, part quantum, and part mystery. And perhaps that is what makes magnetars feel so profound. They are not only violent remnants of stellar death, they are places where the interior of matter is brought into the open, held together for a while against collapse, and made briefly visible to minds as small and curious as ours. Chapter 5: The Strongest Magnetic Fields in the Universe. If you want to understand what truly sets a magnetar apart from every other dead star, you eventually arrive at the most astonishing part of its identity. Magnetism so extreme that it stops being a familiar force and becomes the main architect of the object's behavior. Most people meet magnetism in quiet forms. A compass needle turns, a refrigerator magnet clings to a door. The Earth has a magnetic field, and the Sun has magnetic fields that help drive sunspots and flares. Even an ordinary neutron star has a magnetic field vastly stronger than anything we experience in daily life. But a magnetar stands far beyond all of these. Its field is so powerful that astronomers place magnetars in a category of their own as the most magnetic objects known in the universe. That phrase can sound dramatic in a way that almost weakens it because the scale is hard to feel. A magnetar's field is vastly stronger than Earth's, far stronger than the fields of ordinary neutron stars, and enormously stronger than the strongest magnetic fields human technology can sustain in laboratories. This matters because magnetic fields store energy. In a magnetar, that energy is not a side effect. It is central to the object's life. The field can stress the crust, shape the motion of charged particles around the star, influence the radiation that escapes, and power outbursts that release huge amounts of X-ray and gamma-ray energy. To see why this changes everything, it helps to remember what a magnetic field does at a basic level. Magnetism affects moving electric charges. If charged particles find themselves in a magnetic field, their motion is guided, bent, or confined by it. Around Earth, this produces large invisible structures that trap and channel energetic particles. Around the Sun, magnetic fields sculpt hot loops of plasma. Around a magnetar, the same principle still applies, but under conditions so extreme that the surrounding space becomes a violently constrained magnetic environment. Particles do not simply wander there. They are forced to follow the field in ways that dominate the entire magnetosphere. The magnetosphere is the region around the star where the magnetic field strongly controls matter and radiation. In a magnetar, that region is not calm or empty. It can be filled with charged particles, twisted magnetic structures, and powerful currents. If the magnetic field becomes distorted, wound up, or rearranged, energy can be released outward. In that sense, a magnetar is not just a compact star carrying a magnetic field. It is a whole magnetic system with the star, its crust, and its surrounding environment all linked together. One of the most important ideas in magnetar physics is that the field itself is a fuel source. An ordinary star shines because fusion in its core releases energy. A pulsar can radiate partly by drawing on rotational energy as it slows down. A magnetar, by contrast, is understood to be powered largely by the decay and rearrangement of its magnetic field. That means the field is gradually giving up energy, and that released energy can heat the surface, drive persistent X-ray emission, and trigger episodes of violent activity lasting from weeks to years. This is why magnetars can appear brighter in high-energy light than would be expected if rotation alone were responsible. Their magnetism does work on the star and its surroundings. It builds stresses, distorts the crust, and loads the magnetosphere with energy. When those stresses become too great, some of that energy can be discharged in bursts, flares, or longer outbursts. In a deep sense, the magnetar shines because its magnetic field cannot remain perfectly stable forever. A magnetic field is not only defined by strength, but also by shape. The field around a simple bar magnet is often drawn as a tidy set of loops. And for many stars, that picture is a useful first approximation. But the field of a magnetar may be far more complex. It can include large-scale structure extending outward, local regions where the surface field is stronger than the average, and twisted components in the outer magnetic environment. Those twists matter because a twisted field stores more energy. If the twist relaxes or breaks, the star can suddenly release some of that stored energy into space. This helps explain why magnetars are associated with some of the most violent eruptions seen from neutron stars. The crust and the magnetic field are coupled. If the crust shifts, the field can react. If the field changes, the crust can be strained. The result is not a simple solid body sitting quietly under gravity. It is a magnetic object whose outer layers are under continual tension. In active periods, the field may rearrange on the surface or in the magnetosphere, creating hot spots, altering the star's pulse pattern, and driving short flashes or longer episodes of enhanced emission. In especially dramatic cases, magnetars can produce giant flares, among the most intense bursts known from this class of object. Yet the strength of the field is not important only because it powers eruptions. It also changes the physics of light and matter in ways that sound almost unreal. Under such intense magnetism, the paths and polarization of light can be affected in measurable ways. Observations of strongly magnetized neutron stars have provided evidence that empty space itself can behave differently in these conditions, altering the polarization of light passing through it. This does not mean the vacuum becomes filled with ordinary material. It means that under the rules of quantum physics, very strong magnetic fields can make empty space respond to radiation in a way that is normally far too weak to notice. This is one of the reasons magnetars are so scientifically valuable. They are natural laboratories for extreme physics. In laboratories on Earth, magnetic fields can be made very strong, but not remotely on the scale sustained by a magnetar. Near a magnetar, researchers can study how radiation behaves in intense fields, how matter responds when magnetic forces rival or exceed other influences, and how large stores of magnetic energy are released in violent events. The field can even influence the surface of the star in indirect ways that astronomers can watch. Observations in X-rays have shown that some magnetars develop hot regions on their surfaces during outbursts. These hotspots can move, change size, merge, or fade over time. One likely explanation is that changes in magnetic stress and crustal motion alter how energy is deposited on or just above the surface. In that way, the magnetic field leaves visible fingerprints. Astronomers also estimate magnetar field strengths by watching how these stars spin. A rotating magnetic neutron star loses energy over time, and the rate at which it slows can reveal how strong its magnetic field must be under standard models. This does not give a perfect map of the field, and real magnetars may have more complicated magnetic geometries than the simplest calculations assume. But the slowing of their rotation, combined with their high energy behavior, strongly supports the conclusion that their fields are vastly stronger than those of ordinary pulsars. Another consequence of extreme magnetism is that it can change the balance of forces in the outer layers of the star. In ordinary matter, atomic structure is governed largely by electric attraction and quantum rules for electrons. In a magnetar strength field, magnetic effects become so dominant that atoms and plasmas can behave in unfamiliar ways. The detailed physics is difficult, but the basic point is clear. Matter placed in such a field does not remain entirely ordinary. This helps explain why the phrase strongest magnetic fields in the universe is not just a record book fact. It is the key to the whole object. Without that magnetic intensity, a magnetar would not erupt the way it does, would not glow the way it does, and would not serve as such a powerful testing ground for physics. Its field is not an accessory. It is the reason the star belongs to this special class at all. And yet there is an irony here. A magnetar's magnetic field, powerful as it is, also contains the seeds of its own decline. The field is expected to decay over time. As it does, the most active phase of the magnetar gradually fades. The outbursts become less frequent or weaker, the unusual luminosity declines, and the object may begin to resemble a quieter neutron star remnant. In other words, the same magnetic power that makes a magnetar extraordinary is also what cannot last unchanged forever. That makes magnetars feel almost like brief peaks in the life of stellar remnants. A massive star dies, a compact neutron star is born, and in a small number of cases, the result is an object with magnetic fields so immense that for a while they dominate everything. The star's later life is then shaped by the slow spending of that magnetic wealth. Stress accumulates, light escapes, outbursts flare, surface regions heat and cool, spin slows. The field gradually relaxes. Through all of it, magnetism remains the central story. So when astronomers say that magnetars host the strongest magnetic fields known, they are saying much more than that. These stars win a competition. They are saying that magnetars occupy a physical regime where magnetism becomes one of the main engines of reality. The field stores energy, powers emission, governs particles, distorts the magnetic environment around the star, and may even reveal subtle quantum properties of the vacuum itself. And perhaps that is why magnetars are so compelling to think about at night. Magnetism is something we know from tiny objects in our hands, and yet somewhere in the dark, there are dead stars where the same force rises to such intensity that it can shape light, strain matter, and power eruptions visible across the galaxy. It is a reminder that the universe often takes ordinary ingredients and carries them far beyond anything our daily world prepares us to expect. Chapter 6. Why Magnetars Shake, Crack, and Erupt. A magnetar may look from far away like a small and silent remnant drifting in darkness, but in reality, it is one of the least settled objects in the cosmos, a star whose crust and magnetic field are locked in a long struggle that can end in sudden shaking, cracking, and explosive release. The next question is what the magnetic field actually does to the star over time. The answer is that the field does not simply sit there. It evolves, it shifts, it slowly untwists in some places, and grows more stressed in others. Because the magnetic field threads through the star and extends outward into the surrounding magnetosphere, any change in the field can affect both the interior and the space around the star. This is where the image of a quiet dead star begins to fail. A magnetar is dead only in the sense that it no longer shines by nuclear fusion. Its later life is powered by the stored energy of magnetism, and that energy does not leak away in a perfectly smooth manner. Instead, it can build tension inside the star, especially in the crust, and then release it in bursts. The object is more like a strained system than something truly at rest. The crust is central to this story. Earlier we described it as a solid outer layer made of extraordinarily dense matter. But solid does not mean simple. The crust of a neutron star is likely the strongest solid material known in nature. Yet even the strongest solid can fail if the forces acting on it become large enough. In a magnetar, the magnetic field inside the star is thought to be twisted and wound up, and as it slowly evolves, it pushes on the crust from below and from within. Over time, those magnetic stresses can become too large for the crust to bear quietly. A useful comparison is the crust of the Earth, though only in a very loose sense. On Earth, internal stress accumulates in the crust and may eventually be released in an earthquake. A magnetar may behave in an analogous way, but under conditions vastly more extreme. The crust is not made of rock, and the force doing the stressing is not plate motion but magnetic tension. Still, the basic idea is similar. A solid outer layer resists deformation for a while, stores strain, and then gives way. When that failure happens, astronomers often describe it as a starquake. The star's crust can crack, shift, or deform suddenly. But it is important not to picture a crack opening into empty space the way a crack opens in dry mud. The crust of a magnetar is under enormous pressure and gravity. The failure is more like a sudden rearrangement of a rigid, ultra-dense shell than the formation of a gaping fracture. Instead, the crust yields, slips, or breaks under magnetic stress, and that sudden motion sends energy through the star and into the magnetosphere. That release can happen in more than one way. In some models, the main trigger is the crust itself giving way. In others, the magnetosphere becomes unstable first, and magnetic field lines reconnect, releasing energy outside the star in a process somewhat analogous to solar flares, though again under much more extreme conditions. These ideas are not necessarily rivals. The crust and the magnetosphere are coupled. A shift in the crust can launch disturbances into the magnetic environment above it, and an instability in the magnetic field outside the star can feed back onto the surface. The event we observe may be the visible result of both internal and external processes happening together. This helps explain why magnetar eruptions can be so varied. Some are very short bursts of high-energy radiation, lasting only a brief moment. Some are longer outbursts in which the star brightens and remains unusually active for weeks, months, or even longer. Some involve changes in pulse shape, spin behavior, or surface hotspots. The underlying cause in all these cases is believed to be the release of magnetic stress, but the exact way that stress is stored and then unloaded may differ from event to event. The shaking itself may also leave measurable traces. After especially energetic events, astronomers have found evidence for rhythmic variations in the high-energy emission from some magnetars. One interpretation is that the star or its magnetic environment is ringing, almost like a struck bell, though the physics is far more complex than that image suggests. These vibrations may carry information about the rigidity of the crust, the coupling between crust and core, and the magnetic structure around the star. One particularly interesting clue is the connection between bursts and sudden changes in rotation. Some magnetars have shown small but abrupt shifts in their spin during active periods. These events suggest that the surface and interior are not always perfectly locked in a simple way. If the crust cracks or reconfigures, or if internal stresses redistribute angular momentum, the spin can change slightly. That makes sense in a star whose outer shell is under tension and whose deeper interior may contain superfluid matter that responds differently to stress and motion than the crust does. Heat is another important part of the story. A magnetar eruption is not just a flash in empty space. Magnetic energy can be deposited into the crust and on the surface, warming regions of the star and creating hot spots that linger after the initial burst. Those hot regions can then cool slowly over time. This is one reason some outbursts have a long afterglow in X-rays. The immediate eruption may be brief, but the star keeps radiating the consequences of the event as heat leaks outward. All of this makes magnetars feel less like rigid objects and more like stressed systems hovering near failure. Their magnetic fields are thought to evolve continuously through the crust and core. The field may drift, twist, and decay. Electric currents may move through the outer layers. The crust resists these changes, but not perfectly. The result is a slow loading of strain followed by sudden release. The timescale of stress buildup can be long, while the eruption itself can begin almost instantly. In that sense, magnetars behave like many unstable systems in nature. Long preparation, short discharge. There is also a useful distinction between ordinary persistent emission and eruptive activity. Even when a magnetar is not obviously bursting, its magnetic field may still be heating the star and powering a steady level of high-energy radiation. The star is not truly quiet, it is simply quieter. During an active episode, the same magnetic engine enters a more dramatic phase in which part of the stored energy is released much more quickly. This means a burst is not something totally separate from the magnetar's normal life. It is an intensification of the same underlying story. The magnetosphere plays a major role here because it is where much of the escaping radiation is shaped. Magnetic field lines above the star can become twisted and filled with charged particles. Those particles can scatter radiation, alter the observed spectrum, and help turn magnetic disturbances into visible high-energy emission. If the magnetic configuration becomes unstable and reconnects, energy can be dumped rapidly into particles and radiation. This is one reason eruptions can rise so fast, but the trigger remains a subtle issue. Scientists do not yet treat every eruption as arising from one single mechanism. Some events appear more consistent with crustal failure. Others may be dominated by processes in the outer magnetic environment. It is possible that the distinction is partly artificial, because the two regions are tied together. A magnetar is one object whose dense matter and magnetic field form a single evolving system. This whole process also explains why magnetars do not erupt all the time with the same intensity. Stress has to build. Magnetic geometry matters. Some configurations may remain metastable for long periods. Others may fail in a cascade, where one rearrangement triggers another. That may be why magnetar bursts often come in episodes. A first disturbance may alter the field, which then changes the stresses elsewhere, leading to further bursts before the system settles into a temporarily quieter state. After an eruption, the magnetar does not become normal. It becomes less strained in one particular way, while the deeper long-term evolution continues. Magnetic fields in the interior may still be drifting, currents may still be changing, heat may still be moving outward, the crust may still carry unresolved stresses, so each outburst is both an ending and a continuation. A magnetar does not erupt because it is unstable in a vague or mysterious sense. It erupts because there's a physically understandable source of energy, a medium that can store stress, and a coupling between internal matter and external magnetic structure that allows sudden release. The details are complicated, but the broad framework is solid. Extreme magnetic fields evolve. Solid crusts can fail. Magnetospheres can reconnect. High-energy radiation can carry the result across space. And perhaps that is the most striking part of all. What we call a magnetar burst is not merely an explosion seen from afar. It is the soundless signature of a star under strain, a moment when one of the most rigid objects in the universe yields to the pressure of its own magnetic field. The star shakes, the crust shifts, the magnetosphere flares, and for a short time the hidden tensions inside a dead star become visible. So when magnetars shake, crack, and erupt, they are not behaving like broken stars. They are behaving exactly like stars in which magnetism has become too powerful to remain quiet. Their violence is not separate from their nature. It is the natural consequence of a compact object whose field stores immense energy, whose crust can resist only so much, and whose surrounding magnetic environment is ready to respond the moment that resistance gives way. Somewhere in the dark, a tiny stellar remnant may look still from the outside, while deep within it, the next disturbance is already slowly taking shape. Chapter 7: Giant Flares and the Violence of Dead Stars. A giant flare is what happens when a magnetar stops releasing its stored magnetic strain in small doses and instead unloads a catastrophic amount of energy in a single event, creating one of the brightest flashes ever produced by a dead star. Earlier we looked at why magnetars can shake, crack, and erupt, but not every eruption is equal. Many magnetar bursts are brief and comparatively modest by magnetar standards, even though they would still seem extraordinary next to almost anything in ordinary astronomy. A giant flare belongs to a different category. It is not just another burst. It is the rarest and most extreme expression of magnetar violence, a moment when the star releases energy on a scale so large that even from vast distances it can dominate the high-energy sky for an instant. To understand why giant flares matter, it helps to picture the magnetic field of a magnetar as a system storing enormous tension. For long periods, that tension may be redistributed gradually. The crust may deform a little, the magnetic structure above the surface may shift, and the star may give off ordinary outbursts. But in a giant flare, the star seems to cross a threshold. A large region of the crust may fail, the outer magnetic field may suddenly reconnect and rearrange, or both things may happen together. The event is then not a slow leak but a rapid discharge, like a dam giving way after too much pressure has built behind it. What astronomers actually see during a giant flare has a recognizable pattern. First comes an extraordinarily bright initial spike of high-energy radiation. This first pulse rises very quickly and lasts only a short time. It is the most violent phase of the event, the part that can saturate detectors and flood the surrounding space with gamma rays and X-rays. Then, after that opening blast, there is often a softer tail of radiation that can last much longer. This tail is not smooth. It usually rises and falls with the magnetar's rotation, so the flare appears to pulse as the star turns. That pulsing tail is one of the signatures that helped astronomers recognize giant flares as coming from rotating neutron stars, rather than from some completely different kind of cosmic explosion. This two-part structure tells us something important about the physics. The initial spike seems to reflect a sudden and extreme release of magnetic energy, probably associated with a rapid reconfiguration of the magnetic field and perhaps with crustal failure beneath it. The longer tail appears to come from hot plasma and radiation trapped close to the star by the powerful magnetic field. In other words, the first flash is the violent opening, and the tail is the afterglow of matter and radiation held captive by magnetism near the surface. The field does not merely launch the event, it also shapes what happens after the main flash has already passed. That trapped fireball picture is one of the most elegant ideas in Magnetar science. In ordinary explosions, hot material expands freely if there is enough room and nothing to hold it back. Near a magnetar, the magnetic field is strong enough to confine plasma close to the star. This means the flare can create a glowing reservoir of energy around the surface, and as the star rotates, we see different parts of that glowing region come into and out of view. The flare does not simply flash and disappear. It rings on for a while in a structured and rotating form, as though the magnetic field itself were cupping the hot aftermath in its hands. Only a very small number of classic giant flares have been observed clearly enough for this pattern to be studied in detail. That rarity is part of what makes them so valuable. A giant flare is not a routine behavior seen every week from known magnetars. It is a rare event, and because it is rare, every well-observed example becomes a kind of natural experiment. Scientists compare the rise time, the intensity, the pulsating tail, the energy spectrum, and the later after effects to understand what parts of the process are common and what parts vary from one flare to another. One especially famous giant flare in the early 21st century was so intense that its radiation briefly disturbed the upper layers of Earth's atmosphere, even though the source was still deep within our galaxy. A dead star only about the size of a city, located far across the galaxy, emitted such a powerful burst of high-energy radiation that the effect was measurable at Earth. The event did not threaten life here, but it demonstrated just how immense the flare was. For a brief moment, the energy released by a compact remnant reached across interstellar space and left a detectable mark on our own planet. That same flare also taught astronomers that giant flares are not only bright. During the fading tail, researchers found oscillations in the X-ray light that may represent vibrations of the neutron star itself, or of the tightly linked crust and magnetic field. This idea is remarkable because it suggests that a giant flare can make the whole star ring. In a loose analogy, the flare acts like a strike on a bell, and the star responds with seismic and magnetic motion. These signals are not heard as sound, of course, but detected as repeating changes in the emitted radiation. That possibility matters because the inside of a neutron star cannot be observed directly. We cannot sample one or reproduce its interior in any lasting way on Earth. But if a giant flare excites global vibrations, then the frequencies and patterns of those vibrations can reveal clues about the crust, the strength of the magnetic field, and the way the interior is coupled to the outer layers. In that sense, giant flares are not only destructive episodes, they are diagnostic events. They briefly illuminate the hidden structure of the star by forcing it to respond under extreme stress. Giant flares also matter beyond the study of magnetars themselves, because they can resemble another famous class of cosmic event: short gamma-ray bursts. If a giant flare occurs in another nearby galaxy, the first spike may be bright enough to detect, while the softer pulsing tail is too faint to see clearly. In that case, the event can look like a much more distant and much more powerful explosion of another kind. More recent observations of nearby extragalactic flares have strengthened the idea that at least some short high-energy bursts in the local universe may actually be magnetar giant flares. This is a good example of how extreme astrophysical events can blur into one another when viewed from far away. Up close, a giant flare has a distinct life story. A sudden magnetic catastrophe, an intense opening spike, a trapped and pulsing tail, and sometimes later signs of ejected matter interacting with the environment around the star. Seen from millions of light years away, much of that detail is lost. What remains may be just a brief flash. Distance erases context. There's also growing evidence that giant flares do not only release light. They can hurl matter outward as well. A violent magnetic rearrangement may drive a cloud of particles away from the star at tremendous speed. As that outflow expands and eventually collides with surrounding gas, it can create shocks and additional high-energy emission. This gives giant flares a second life after the first flash, because the material launched by the event may continue interacting with its environment long after the initial radiation has passed. All of this shows that a giant flare is not a simple burst from a single point in space. It is a chain of linked processes. Magnetic stress builds over time. A trigger occurs, perhaps in the crust, perhaps in the magnetosphere, perhaps in both together. A huge initial pulse of radiation is released. A hot, magnetically trapped tail may follow. The star may vibrate. Matter may be ejected. The surrounding medium may respond. Each stage tells us something different about the object. This also helps us understand why giant flares are treated with special respect in high-energy astronomy. They are not merely larger versions of ordinary magnetar bursts. They are threshold events, moments when the magnetic system of the star undergoes a major global failure or rearrangement. In smaller bursts, the disturbance may remain local. In a giant flare, the disturbance seems to involve a much larger portion of the star and its magnetic environment. And yet giant flares do not make magnetars arbitrary or chaotic. The shape of the light curve, the rotational pulsing in the tail, the evidence for magnetic confinement, and the possible seismic ringing all point toward physical structure rather than random destruction. A giant flare is violent, but it is not meaningless. It is a comprehensible event governed by the same laws of matter, magnetism, radiation, and gravity that shape the rest of the universe, only pushed into a regime of unusual intensity. Perhaps that is why giant flares are so unforgettable. They reveal that even after a massive star has died, its remnant can still produce some of the most dramatic flashes in the cosmos. The star is small, cold by stellar standards, and no longer powered by fusion. Yet because of magnetism, it remains capable of astonishing acts of release. A giant flare is the proof. It is the moment when a dead star briefly becomes one of the brightest things in the sky, not by reigniting, but by surrendering part of the magnetic strain it has carried in silence. So when we talk about the violence of dead stars, giant flares are the clearest example of what that phrase means. They are sudden, rare, and intensely revealing. They show that a magnetar is not merely an endpoint of stellar evolution, but an active and unstable object whose strongest moments can teach us about crustal failure, magnetic confinement, stellar vibrations, and the hidden connection between distant compact remnants and the high-energy flashes we detect across the universe. Chapter 8: Magnetars, Pulsars, and Fast Radio Bursts. Magnetars become even more fascinating when we compare them with pulsars and then connect both of them to one of the strangest signals modern astronomy has ever found: fast radio bursts, flashes so brief and so intense that they force scientists to rethink what a compact dead star might be able to do. A pulsar is not a completely different kind of object from a magnetar. Both belong to the broader family of neutron stars, which are compact remnants left behind after massive stars die. The key difference is not in their basic origin, but in what dominates their later behavior. In a pulsar, the most obvious feature is usually the regular sweep of radiation caused by rotation. The star spins, beams of radiation emerge from regions linked to its magnetic poles, and if one of those beams crosses our line of sight, we detect a pulse. That is why pulsars can seem so clock-like. Their most famous signature is repetition. A magnetar can also pulse. In that sense, some magnetars are pulsars too, because they are rotating neutron stars whose radiation changes with spin. But magnetars are unusual members of that broader population. Their magnetic fields are stronger, their high-energy behavior is more violent, and their emission is often less stable and less neatly regular than the classic image of a lighthouse-like pulsar. A useful way to think about the distinction is this: pulsars are usually introduced through their rotation, while magnetars are usually introduced through their magnetic stress and eruptive activity. The categories overlap, but they do not emphasize the same physics. This matters because it shows that neutron stars are not all built to announce themselves in the same way. Some are best known as steady cosmic beacons, some are best known as unstable magnetic powerhouses, and some objects blur the boundary. A few magnetars have been detected producing radio pulses, which means they can temporarily behave in ways that resemble more ordinary radio pulsars. That was an important clue, because it suggested that the family resemblance between pulsars and magnetars is not just theoretical. Under the right conditions, a magnetar can step into radio behavior that looks surprisingly familiar, even if the underlying magnetic environment remains much more extreme. To see why this connection became so important, we have to introduce fast radio bursts. A fast radio burst is a very short flash of radio emission arriving from space. The burst lasts only a tiny fraction of a second, but during that moment it can release an extraordinary amount of energy in radio waves. For years, fast radio bursts were one of the great puzzles of astronomy. They were clearly real. They were coming from other galaxies, and in many cases they repeated, which meant they could not all be one-time catastrophes. The challenge was to find a source powerful enough, compact enough, and active enough to explain them. Compact dead stars quickly became leading candidates because a very short burst implies a very small source region. If a signal rises and falls in a tiny amount of time, the object producing it cannot be too large, otherwise different parts of it would not be able to act together quickly enough. Neutron stars fit that requirement naturally. They are small, dense, and capable of intense magnetic and rotational phenomena. Pulsars already showed that neutron stars can produce coherent radio emission. Magnetars already showed that neutron stars can store huge amounts of magnetic energy and release it suddenly. So even before a direct link was found, many scientists suspected that some kind of neutron star might be involved. The breakthrough came when astronomers detected a burst from a known magnetar inside our own galaxy that looked like a fast radio burst. During an active episode, it emitted a powerful radio burst at the same time as an X-ray burst. This was the first clear case in which a magnetar was caught producing a burst with the essential character of the mysterious flashes previously seen only at much greater distances. That event did not prove that all fast radio bursts come from magnetars, but it did show decisively that magnetars can produce at least some of them. It was a major turning point because for the first time the connection moved from plausible idea to observed fact. That discovery mattered for another reason as well. Before it, magnetars were often discussed mainly in the language of X-rays and gamma rays, while fast radio bursts belonged to a different observational world centered on radio telescopes. The galactic event tied those worlds together. It showed that a magnetar outburst can produce a radio signal bright enough to resemble the fast radio bursts seen in other galaxies, while also being accompanied by high-energy activity. That means the radio flash is probably not an isolated trick of geometry. It may be one visible part of a larger disturbance involving the star's magnetic field, magnetosphere, and perhaps its surface layers as well. Even so, the story remains more complicated than a single simple answer. Not every magnetar is known to produce fast radio bursts. Not every fast radio burst behaves the same way. Some repeat often, some repeat rarely, and some have not yet been seen to repeat at all. Some come from young star-forming environments, which fits well with the idea of young magnetars born from massive stars. Others seem to arise in more complicated surroundings. So the current picture is not that magnetars explain everything effortlessly. It is that magnetars are now one of the strongest and best supported source classes in the field, especially for repeating bursts. While some events may still involve additional channels or special circumstances, the comparison with ordinary pulsars is especially helpful here. Pulsars already taught astronomers that neutron stars can generate beams of radio emission with remarkable regularity. But the pulses from a classical radio pulsar are usually tied directly to the star's steady rotation. They repeat every turn like a beacon. A fast radio burst is different. It is not usually one sweep in a regular train. It is more like a sudden shot of radio energy, often much brighter and less predictable. That contrast suggests that fast radio bursts are not just ordinary pulsar beams viewed in a different way. They seem to require a more explosive or more unstable process, which is one reason magnetars became such compelling candidates. At the same time, pulsars have not become irrelevant to the story. They remain part of the conceptual bridge. Because pulsars demonstrate that neutron stars can make powerful radio signals, they help show that neutron star magnetospheres are capable of producing ordered radio emission at all. Magnetars then extend that picture into a more violent regime. One way to say it is that pulsars provide the proof of principle for radio beaming from neutron stars, while magnetars provide a way to inject much more magnetic energy into brief and dramatic events. The two classes are not rivals so much as neighboring expressions of what compact stellar remnants can do. There is also a deeper lesson in the timing of these signals. A fast radio burst lasts for such a short time that whatever produces it must act with astonishing efficiency. A magnetar does have that kind of efficiency available. Its magnetic field stores tremendous energy in a compact volume, and when the magnetic structure shifts suddenly, the surrounding plasma and radiation field can respond almost instantly. The exact emission mechanism is still being worked out, and several models remain under discussion. But the broad physical setting is now much less mysterious than it once was. Scientists no longer have to wonder whether a magnetar can produce such a burst in principle. We know that at least one did. So where does that leave the relationship among magnetars, pulsars, and fast radio bursts? The cleanest answer is that pulsars and magnetars are related kinds of neutron stars, with pulsars defined mainly by their regular rotational pulses and magnetars defined mainly by their extreme magnetic fields and eruptive behavior. Fast radio bursts are brief flashes of radio energy that, in at least some cases, can be produced by magnetars during active episodes. Pulsars helped prepare astronomers to believe that neutron stars could make strong radio signals. Magnetars supplied the missing ingredient of explosive magnetic energy. Together they form a connected picture rather than three unrelated mysteries. And perhaps that is what makes this chapter so satisfying. A dead star that once seemed to belong only to the world of X-rays and gamma rays now turns out to be part of the explanation for one of the most puzzling radio signals in the universe. The regular beacon of a pulsar, the magnetic unrest of a magnetar, and the sudden flash of a fast radio burst all become parts of one broader story about what matter, magnetism, and motion can do when a star ends but does not entirely fall silent. Chapter 9. How we detect and study magnetars. A magnetar is one of the most extreme objects in the universe, but the strange thing is that astronomers do not usually find one by seeing a tiny star directly. They find it by catching its behavior, following its signals across different kinds of light, and slowly turning those clues into a physical picture of an object too small and too distant to observe in any ordinary way. That is an important place to begin, because a magnetar is not something that appears in a telescope as a neat glowing sphere with visible details on its surface. Even with our best instruments, it is far too distant and far too small for that. Instead, astronomers detect a magnetar through the radiation it emits, the way that radiation changes with time, and the environment around it. In other words, a magnetar is studied less like a photographed object and more like a solved signal. The first step is often discovery through a burst. Many magnetars come to attention because they suddenly emit a flash of high-energy radiation. These flashes can appear in X-rays or gamma rays and may be noticed by space telescopes that monitor large portions of the sky for sudden transient events. Because such bursts can happen without warning, wide-field instruments are especially important. They act as watchmen, scanning the sky continuously and announcing when something unusual has happened. A brief burst may last only moments, but it can be enough to alert the rest of the astronomical community that a compact and highly energetic source has awakened. Once that alert is issued, more focused telescopes turn toward the source. This is where follow-up observation becomes essential. A discovery instrument may reveal that a burst has occurred, but to understand the source, astronomers need sharper imaging, better timing, and more detailed spectroscopy. X-ray telescopes with higher angular resolution can localize the source more precisely on the sky. That helps determine whether it lies inside a known supernova remnant, near a star cluster, close to a region of dust, or in some more isolated setting. It also allows astronomers to separate the magnetar from other nearby sources of X-rays in crowded regions of the galaxy. Localization matters because context matters. If a newly discovered source lies inside the debris of an exploded star, that supports the idea that it is a young neutron star remnant. If it sits near the center of the galaxy, the surrounding environment may complicate the observation by adding dust scattering, background radiation, and overlapping sources. If it is associated with a known stellar nursery, that may say something about its origin. So even though the magnetar itself is tiny, astronomers learn a great deal by seeing where it lives. After the position is pinned down, one of the most important things astronomers measure is the spin period. Magnetars are rotating neutron stars, and their radiation often varies in a regular way as they turn. By recording the arrival times of X-ray pulses over and over again, astronomers can determine how long the star takes to complete one rotation. That spin period is one of the basic fingerprints of the object. But the story does not stop there. By continuing to monitor the source over days, months, and years, astronomers can also measure how the spin changes. If the star is slowing down in a way consistent with strong magnetic braking, that becomes one of the key pieces of evidence that the source belongs to the Magnetar class. This method is called timing, and it is one of the most powerful tools in neutron star astronomy. Timing does more than reveal the rotation rate. It can show whether the star spins down smoothly or irregularly, whether outbursts are accompanied by sudden changes in rotation, and whether the pulse shape itself changes over time. A magnetar in a quiet state may show one pulse pattern, while after an outburst it may show a different one because the hot regions on its surface or the structure of its magnetosphere have changed. So, timing is not only a way to count rotations, it is a way to watch the star's outer layers and magnetic environment evolve. Spectroscopy adds another layer of understanding. Instead of asking only how bright the source is, spectroscopy asks how that brightness is distributed across different energies. A magnetar spectrum can reveal whether the radiation looks more thermal, which would suggest hot surface emission, or more non-thermal, which points toward magnetospheric processes and energetic particles. During outbursts, the spectrum may harden or soften, hot regions may appear or fade, and additional components may become visible. By following these spectral changes, astronomers infer how energy is being deposited into the crust, how the surface is cooling, and how the magnetic environment is scattering or reshaping the escaping radiation. Imaging is also more informative than it might first seem. Even when the magnetar itself appears as a point source, the region around it can carry clues. In some cases, diffuse X-ray emission appears nearby because dust between the star and Earth scatters some of the radiation. This can create halos or rings that expand with time after a bright outburst. Those rings are beautiful, but they are also useful. They can help astronomers map dust along the line of sight and sometimes improve estimates of the magnetar's distance and environment. In other cases, diffuse emission may arise from particles flowing away from the neutron star or from the surrounding remnant of the original supernova explosion. Distance itself is one of the harder things to measure, and astronomers often have to combine several indirect methods. They may compare the source with surrounding gas and dust, study absorption in the X-ray spectrum, examine whether the magnetar is associated with a known remnant or star cluster, or use radio measurements when available. There is rarely a single perfect answer. Instead, distance is often constrained by building a consistent picture from multiple kinds of evidence. This is common in astronomy. The farther and more compact the object, the more often truth comes from overlap among several imperfect clues rather than from one direct measurement. Radio observations add a fascinating dimension. For a long time, magnetars were primarily discussed as X-ray and gamma-ray sources, but some have also been detected in radio waves. When that happens, radio telescopes can measure pulse shapes, polarization, scattering, and changes in brightness with great precision. Radio signals can also probe the material between the magnetar and Earth, because the signal is dispersed and distorted as it travels through ionized gas. From this, astronomers learn not just about the source, but also about the medium the signal crossed. In unusual cases, radio bursts from magnetars have helped connect them to the broader mystery of fast radio bursts. Polarization is another especially revealing tool. Light is not only defined by its energy and brightness, but also by the orientation of its electric field. In strongly magnetized environments, that orientation can carry information about the structure of the magnetic field and the processes that produce the radiation. Measuring polarization from a magnetar is technically difficult, but when it is possible, it provides something close to a map of the geometry of the emission region. It also helps test how light behaves in extremely strong magnetic fields, where even the vacuum itself can influence what we observe. In that sense, polarization is one of the most subtle and powerful ways of studying a magnetar, because it lets astronomers examine not just where the light came from, but how the surrounding physics shaped it. Long-term monitoring is just as important as dramatic discovery. A magnetar can change on timescales of seconds during a burst, but it can also evolve over months and years after an outburst. Surface hotspots cool, the pulse profile changes, the spin-down rate may drift, the spectrum softens, the source gradually relaxes toward a quieter state. Following that evolution teaches astronomers how magnetic stress is released, how heat flows through the crust, and how the magnetosphere reconfigures after a disturbance. A single burst may announce the source, but long-term observation is what turns that announcement into understanding. Multi-wavelength observation is therefore essential. No single kind of telescope tells the whole story. Wide-field high-energy instruments are good at catching the first sign of trouble. Focused X-ray observatories provide localization, timing, and spectroscopy. Radio telescopes reveal pulses and propagation effects. In rare cases, measurements of polarization or very high-energy emission open yet another window. The most informative studies happen when these observations are coordinated, because magnetars are variable, and their different signals do not always appear at the same time. What one telescope sees as a flash, another may see as a changing pulse pattern, and another as a radio counterpart or a fading after effect. This is why modern magnetar astronomy often works like a global listening network. One instrument notices a burst and sends an alert. Others respond quickly. Some gather precise X-ray timing. Some gather spectra. Some look for radioactivity. Some continue watching long after the excitement fades. Bit by bit, the observations are combined into a picture of what happened. The magnetar itself remains too small and distant to visit directly, but its changing signals create a record detailed enough to expose its rotation, magnetic unrest, surface heating, surrounding dust, and even parts of its internal response to stress. So when we ask how astronomers detect and study magnetars, the real answer is that they do it by turning light into structure and change into evidence. They catch bursts, locate sources, measure spin, track slowing rotation, examine spectra, monitor cooling, map surrounding dust, search for radio pulses, and compare observations across different kinds of telescopes. A magnetar is not studied through one dramatic image. It is studied through patience, timing, comparison, and the careful interpretation of signals that travel for thousands of years before they reach us. And perhaps that is what makes this chapter quietly beautiful. The object itself is hidden almost beyond imagination. Yet by listening closely enough to its flashes and rhythms, human beings can still learn what kind of star it is, how it spins, how it cools, how it erupts, and where it lives. We do not see a magnetar the way we see the moon or a planet. We reconstruct it from traces, and somehow those traces are enough. Chapter 10. What magnetars reveal about the universe. By the time we reach the end of this story, a magnetar no longer feels like just one unusual object in deep space. It begins to feel like a concentrated lesson in how strange, powerful, and unexpectedly coherent the universe really is. At first glance, a magnetar might seem too rare and too extreme to teach us anything general. It is a special kind of neutron star, born under unusual conditions, carrying magnetic fields far stronger than anything human beings can create, and releasing energy in violent bursts that most stars never produce. But this is exactly why magnetars matter. Nature often reveals its deepest rules most clearly at the extremes. When a system is pushed far enough, hidden physics rises to the surface. A magnetar is one of the places where that happens. One of the first things magnetars reveal is that the universe does not separate the ordinary from the extraordinary as sharply as we do. Magnetism is familiar on Earth. It guides a compass, stores information, and helps power the technologies of daily life. Yet in a magnetar, the same force becomes one of the main engines of the object's life. The lesson is not that magnetism changes into something else. The lesson is that familiar laws can produce astonishing outcomes when matter, gravity, and energy are pushed to extremes. The universe does not need different rules to create wonder. It only needs room to use the same rules more fully than our everyday world allows. Magnetars also reveal that a star's death is not always an ending in the simple sense. In ordinary language, a dead star is like something exhausted and inactive, as though the interesting part has already passed. But a magnetar shows that the remnant can become a new physical system with its own afterlife. Fusion has ended, but magnetic energy remains. Stress remains, heat remains, motion remains. The object continues to evolve, brighten, cool, crack, flare, and interact with its surroundings. In that sense, stellar death is not always silence. Sometimes it is transformation. A magnetar also reveals something profound about matter itself. Most of what we call matter in daily life is understood through chemistry. We speak about atoms, molecules, solids, liquids, and gases. But inside a neutron star, that familiar language begins to fail. A magnetar reminds us that chemistry is not the deepest description of matter. It is a surface description, valid under the gentle conditions of planets and ordinary stars. Under extreme compression, matter enters states in which atomic structure disappears. Neutrons dominate, quantum behavior becomes collective, and the deepest core may hold forms of substance that remain uncertain even now. That is a humbling lesson. The world we know is only one version of how matter can exist. Because of that, magnetars help astronomy connect with nuclear physics and particle physics. They force us to ask what matter does when gravity squeezes it beyond ordinary intuition. They force us to ask how pressure, density, and quantum rules interact in the deep interior of a compact star. The answer is not yet complete. Astronomers still debate what happens in the innermost core of neutron stars and how compressible that matter really is. But that uncertainty is itself revealing. It means magnetars are not only objects to be described. They are laboratories for questions that cannot yet be answered anywhere else. Their magnetic fields reveal something just as important. In a magnetar, those fields shape the star's emission, confine plasma, stress the crust, and alter the behavior of particles and light near the star. What magnetars reveal, then, is that magnetism is not a decorative feature of astrophysics. It can be a dominant source of structure and energy in its own right. This becomes even more striking when we consider what very strong magnetic fields may do to light itself. In daily life, empty space seems like a simple stage on which events unfold. But observations of strongly magnetized neutron stars have suggested that under extreme conditions, the vacuum around such an object may affect the polarization of light in measurable ways. In other words, what looks like emptiness is not always passive. Under sufficient stress from extreme fields, even empty space begins to show subtle physical behavior. That is a remarkable idea. It means a magnetar can act as a place where the distinction between matter, radiation, and the structure of apparently empty space becomes more subtle than common sense would ever predict. Magnetars also reveal something about scale. They are tiny by astronomical standards, yet they can influence regions of space far beyond their own size and send detectable signals across a galaxy or beyond it. This is one of the quiet patterns repeated throughout astronomy. Small objects can have enormous consequences when their density, field strength, or energy concentration is high enough. A magnetar does not need the size of a nebula or a galaxy to matter. It carries enough intensity in a compact form to announce itself over astonishing distances. This is one reason the connection between magnetars and fast radio bursts became so important. For years, fast radio bursts seemed almost too strange to classify. They were brief, bright, and difficult to explain. When a galactic magnetar was caught producing a burst with the essential character of a fast radio burst, it showed that these compact remnants could be part of the answer. That discovery revealed something broader than the source of one class of signals. It showed how different parts of astronomy can suddenly connect. A neutron star, known for X-rays and gamma rays, turned out to be relevant to one of the biggest radio mysteries in the sky. The universe often behaves that way. Separate puzzles turn out not to be separate after all. Magnetars reveal something important about how science works too. No one can travel to one, touch one, or peel back its layers directly. Everything we know comes from traces. We detect bursts, measure pulse timing, study spectra, follow changes in brightness, examine polarization, and compare models with observations. From those indirect clues, a picture emerges. That picture is incomplete, but it is real. This is one of the most beautiful habits of science. It learns to know the inaccessible through consistency. A magnetar cannot be seen in detail, but it can still be understood through the coherence of the signals it sends. That process also reveals the limits of our knowledge, and those limits are valuable. We still do not know every route by which magnetars form. Recent work even suggests that some may not come from the standard story of an ordinary supernova explosion at all. We still do not know exactly how their deepest magnetic fields are arranged, how the innermost core is composed, or whether all fast radio bursts arise from magnetars. We still debate the precise trigger of many eruptions and the detailed mechanism that produces some of their most intense signals. None of this weakens the subject. On the contrary, it is part of what magnetars reveal about the universe. Reality is understandable, but not exhausted. The cosmos invites explanation without becoming simple. Another lesson is that the universe preserves structure even inside violence. A magnetar is a violent object. It erupts, shakes, and sometimes releases astonishing amounts of energy. Yet that violence is not random. It follows patterns. Bursts have characteristic timescales. Giant flares have recognizable structure. Rotational timing carries information. Surface hotspots migrate and cool in physically meaningful ways. Even the most dramatic events become legible when observed carefully enough. Magnetars therefore reveal a reassuring truth about nature. Extremes are not the opposite of order. They are often the place where order is hardest to see at first, but most rewarding to uncover. In a deeper sense, magnetars reveal that the universe is layered. The sky first appears to be a collection of bright points and dark gaps. Then astronomy shows that stars have life cycles. Then compact objects reveal that stellar remnants can be more extreme than ordinary stars. Then magnetars show that within those remnants, matter, magnetism, radiation, and space-time itself can interact in ways that are far from intuitive. Each layer does not replace the one before it. It deepens it. Magnetars teach us that behind the visible sky there is a hierarchy of hidden worlds, each more demanding and more beautiful than the last. And perhaps this is the final lesson. A magnetar reveals that the universe is not strange in a careless or chaotic way. It is strange in a disciplined way. It allows objects so dense that atoms are crushed apart, fields so strong that they dominate a star's behavior, and events so bright that they can briefly reshape our understanding of the sky. Yet all of this still arises from lawful processes that patient observation can gradually uncover. The universe is more dramatic than common sense expects, but also more intelligible than fear would suggest. So what do magnetars reveal about the universe? They reveal that ordinary forces can become extraordinary under the right conditions. They reveal that the deaths of stars open new chapters rather than simply closing old ones. They reveal that matter has deeper forms than chemistry alone suggests, that magnetism can rival gravity as an organizing power, that empty space may not be as empty as it appears, and that distant flashes can connect whole fields of astronomy in a single insight. They reveal, above all, that reality is larger than the version of it we evolved to see. And that is a gentle thought to end on. Somewhere beyond the reach of daily worries, tiny dead stars are still carrying out this hidden work, testing the limits of matter and light in silence. You do not need to hold all of it in your mind at once. It is enough to know that such things exist, and that the universe, even at its most extreme, remains something that can be slowly learned, quietly wondered at, and finally let wash over you like a distant, steady dark. And now, my friend, we've reached the end of our journey through the strange and powerful world of Magnetars. I hope this quiet trip through dead stars, magnetic storms, and the deeper structure of the universe helped your mind slow down a little tonight. And if you're still awake, you can stay with me a little longer and choose another video for the next calm journey through space and science. But if sleep is finally beginning to find you, then just let yourself drift. Thank you for being here with me tonight, and sweet dreams among the stars.